Welcome everybody to our PIMC Labs webinar. Today I'm excited to be talking with Will Dean. I met Will when he was still living in Berlin, and now he lives in Austria. So Will, welcome and thanks so much for coming on.
Thank you so much for having me.
So I'm curious in general and also about you, how you got your start with Bayesian modeling. How did you discover it? What was your origin story?
So I think my connection to Bayesian statistics really started in academia. I did statistics both in undergraduate as well as graduate. And my university in Boston University, had some ties to kind of the Bayesian world. I think that kind of got on my radar. I think similar to a lot of kind of other programs in education, the frequentist side is very focused on. But when I got into industry then, I started to just toy around with some of this knowledge that I may have gained and stumbled upon PIMC kind of through practice. So long story short there, but then ended up using it in industry and kind of started my journey.
Very cool. Yeah, and welcome everybody who is joining live. We want to try a new thing that we haven't tried before, which is polls, just to get to know you a bit better. So the first one is where you're all from. So hopefully you see something where you can click on. Oh yeah, okay, that is working. So North America and Europe. Okay. Yeah, 70%, 60% Europe, 40% Europe, and South America. Really cool. Well, welcome from where you are. Then the other question I was curious about is whether you have any experience with PIMC. Have you used PIMC before? Are you a user or just curious? Wow, interesting. It is 50-50. I would not have expected that. Amazing. Really good to see people who are not familiar yet, but curious what you can do. And I guess prefacing a little bit what Will is kind of talking about, when he told me about the application, I was like, damn, that sounds really, really cool. And it's definitely something that I and a lot of other people will be interested in. And it goes to show that like Bayesian modeling doesn't have to be involved in terms of like building your own custom models. Sometimes you just find the right one and can just reuse that. So last question is whether you have whether you're in academia or in industry. So academic research, are you doing a PhD? Firmly in the industry camp. Yeah, fascinating. Okay, I guess with the topic of calendars, that makes sense. So thank you all for voting. And yeah, let's get started with the presentation. Will, take it away.
Sounds great. I like that polling idea. It's nice. So let me get started. Let me share my screen. Should see my slides.
Yep, that's coming up.
Okay, so this is the title that I think was being presented everywhere. So I've been playing around with calendar data a lot, and I've been working on a model that I call the latent calendar. And I'll go a little bit into of course, the details. So I'll just give the origin the name, but it's a way to model weekly calendar data, and it uses latent components. So a little bit about myself. Hinted at, I studied mathematics, statistics, and I've been working in industry as a data scientist for the last 4 or 5 years now. I currently I'm on the marketing team for FREENOW, which is a taxi ride-hail provider in Europe. Kind of work all throughout Europe. But my interests are Bayesian statistics and anything that's really tinkering around with data, software. So PIMC fits the bill. Love the kind of customization there, and the fact that you can generate data, I think is very, the workflow is kind of always scratches the itch of mine. And then about this talk, I want to motivate the use of latent Dirichlet allocation. So a typical text modeling technique for using for modeling weekly calendar data. And I want to show off some of the insights that you can kind of get from doing this. A lot of them are just derivations of LDA. I just how I like to toy around with stuff. I want to present the package that I've created for this, so you can hopefully do something with it yourself. And since I'm working in marketing, I want to show you a little bit about how it fits into that process. So to motivate the problem, I'm going to showcase a similar data set to what I was initially working with. So here is looking at Chicago bike trips. So this is a slice of the data set from May 1st to July 30th. And I'm going to kind of focus on these two stations. So that I've highlighted them on this map here. One is over by the lake, and then one is over by the river, over by the Willis Tower. Both are some spots, but as you can imagine, there may be some similarities to differences. And Divi is just the name of it if I slip there, but this is a bike sharing a data set. So each one of the rows is indicating a trip on one of these bikes. So someone going from A to B, and there's some information that is provided in this kind of data set. But only thing that I'm looking at is just the timestamps. So I'm associating the timestamp. So here's just when a trip started, and what is the association with one of the stations. This is timestamps come up everywhere. You know, when you pull down from a database, you have a slice of data set and no clue what timestamps are. So they're everywhere, but you know, they're kind of just staring you in the face sometimes. I think the interesting thing here is that timestamps always provide this additional information. When you have a full date and the time, you always know the date of the week and the hour of the day. So to get away from just looking at rows of data all the time, I always like to go into a visual. So this was the data set and kind of the motivation that I looked into. So these are two calendar slices. I'm using a Monday-based start of the week. So Monday, Tuesday, and then the weekend is going to be this last bit. But without knowing anything about these two stations, you can already kind of see that this slice and look into the data shows some differences. And this is what I was really curious about when looking at kind of a slice of the user base I was working with. For instance, these stations all have users that are going to be working with them. So if you have this one on the left, you see some kind of commuter behavior, something that is very apparent here, but then less so here. This was, again, this station that was on the lake. If you're commuting, say, you might not be commuting from here, but you might be commuting from kind of where the buildings are. And when you're looking at a user's perspective, often you don't have that much data. And I think it's interesting that even though you may have only one point, if you have a point in, say, the middle of the night, it provides a lot of information, especially when you have the case of each data point is signifying that someone is going from A to B. So this was a slice that I think it was very characteristic to an individual. So I wanted to look into this. So the modeling process, which I really like with PyMC, is that you are really focusing on the data generating process. So with this, I wanted to try to visualize and generate the data that would make this calendar. So here, I'm seeing that there's two dimensions. There's the day of the week, and then there's the time of the day. And for those who are not that familiar with PyMC, or those who are, this should be fairly straightforward, but to explain it, there's the day of the week. That's the dimension that I'm trying to just relate with a categorical variable. So this would be taking something from 0 to 6. And then the time of the day was going to be some value between 0 and then the hours of the day. So this is just a crude example, but this is something that could generate this calendar potentially. But since it's all uniform distributions, it doesn't look anything like the data set that we're looking into. But I think this is a interesting start because, and the flexibility that PyMT provides is that we can switch out some of the building block distributions to try other things. So some alternatives that I was thinking about was for the time of day, we have, this is 0 to 24. However, we may be able to use some type of cyclical distribution that could be interesting, maybe a normal that's clipped or something arbitrary, but it has some flexibility here. I think one of the difficulties that I saw was that this is a discrete variable, and then this is a continuous. So I had to jump to see, instead of having a fully continuous time of day, I can use a categorical. But with both of these as categorical, it's easy enough to just lay them all out in a row. So there would be laying out all Monday, followed by all Tuesday, all Wednesday. And if I want to do any reshaping, I can just do that. So this is a just through the PyMC API. It's very easy to do. I have that kind of one dimension for 24 times 7. And if I want to look at the day of the week or the time of the day, I can just derive that using these vector calculations and the operations that will also work on these objects. So I'm not going to show the visual here because you can probably imagine these are just another kind of uniform. So it's not going to have any similarity to or any kind of progress towards what we're working towards. However, I want to talk about this discrete approximation that I think is interesting. So we saw some overlaps in the events that were happening. And here, instead of these dark gray regions, I just bin them and I put them into a displaying them through colors. So we can see that here. These are the two stations that we were discussing. And we can still, with this approximation, see these differences. We see some commuter-like behavior, and then in this one, kind of more weekend heavy, but then also some sporadic kind of trips happening here. And we can do that and switch this into our model assumptions. So people familiar with distributions, categorical is just the kind of a single use case or the single base example for multinomial distribution. And we're just conditioning on the number of events here by incorporating them into our multinomial. And like I mentioned before, we can use these vector operations to do some reshaping if we want to. Since this n is already baked into this, we only have to sample once, which is kind of nice. But I think that this is an interesting start, but I like the Bayesian point of view and the workflow for problem solving because you have to really think about what's going on. So the data set that I was working with is working with people traveling around. But if you talk to anyone or you think about your own self, you can see that there's kind of many behaviors that someone can take. Sometimes you play the role as a work commuter. Sometimes you go on vacation and you're a tourist and you have a little bit of flexibility on your schedule. And some other times you have this weekend explorer. I don't know, some of these personas that may be pushed on with some group of people. But through my API, I can just kind of describe some arbitrary activities, maybe morning, afternoon, weekends, and I can display these also on this calendar. And like I mentioned, people can be one of them, some of them, or all of them. We're leaving out that you're none of them because maybe just some noise at the end, but you can imagine if there's enough, then enough kind of categories, and someone will fall into maybe at least one of them. And if they're only one of them, then it kind of assumes that there's a low probability that they're kind of the other ones. So with these kind of personas, these arbitrary personas in mind, I want to re-look at this generated process of the multinomial distribution. So this is now viewing this as a mixture of multinomials. So I had these three behaviors here: morning, afternoons, weekends, which I stored in a data frame, and I can just look at the number of behaviors. And the generating process here is that for each trip someone takes, it'll be coming from one of the behaviors. So then there's this probability of which one it's going to be associated with. And then now this is going to be the kind of the category which they belong to. I'll have a prior then and a distribution that's going to be representing each one of these. So I'd pick from one of these, and then I'd sample from the mornings and so forth. And we can kind of go back to this same last line. This is this new material. And we now have a generating process for a model. And interestingly enough, you sample 6 times here, and with some of these parameter values set in a somewhat all right way, you have something that starts to look like our data set. So these would be 6, say, stations that are having 500 trips associated with them. And we can see that the sample 1 might be the more leaving for work type of behavior. And then sample 2 has a little bit of this weekend behavior, and then maybe a little tad bit here. And then the sample 3 has a little bit more of that compared to, say, sample 2, and so forth. But if we knew these values here, as well as what are these kind of corresponding components, then we might be able to have a compelling generating process, and it might look similar to our data. But the cool thing is that latent Dirichlet allocation is just a mixture of multinomials. I pulled this from the Wikipedia page, and you can see that it's very similar to that code we just wrote. There's the Dirichlet, and then a multinomial. There's kind of a different formulation, but it basically what's happening. And I think the great thing is that LDA is implemented in many different libraries. There's ones that scale really easily to large data sets, and then of course there's one kind of in sklearn, and the most used package for machine learning. So to take advantage of what is available, I deviate a little bit from the PyMC side of things and just focus on the implementation that I first had using the latent Dirichlet allocation from sklearn. So when you use this API, you get a transform method and a fit method that will learn these components. And then what I built in here is just this information that I want to derive from on top of it. So these components are pseudo counts. So if I do a little transformation here, I can get a probability distribution on each one of the components. And I can use a use of the transform and these components itself to make a calendar distribution. So this would be a distribution for each calendar. So marginalizing out means it's just disregarding how many components are happening and getting back to that original space, that original distribution that I was interested in. And this last bit, which I put in here, was just since there will be a certain number of components, looking at how probable is each one. So the process then becomes defining a vocabulary using the typical LDA jargon. And so that vocabulary comes from timestamps. I use this timestamp that was here to give the week, day of the week, and the hour of the day. And we can lump these together and have a single variable here. Of course, these are all associated with stations then, in this case. And then we can aggregate to the documents. And the documents here are the stations. I have the two that were being shown before. Here are the vocabulary that come from the timestamps. And each one of these are reflecting the counts for the number of trips that happen. So if I sum up over this whole row, I would see the total number of trips that happen. Interestingly enough, this is a kind of a massive reduction in data. So we have this 6.2 or about 6 million rows before, and this just goes down to this almost 1,500, and all of these will sum up to that 6 million. Here I'm just showing the, this is the trip level data set, and I'm showing my API that I built out into the latent-calendar package in order to get to this. It's a very simple process coming from timestamps. So this right here is the key here, and this is what is turned in here based off of kind of the defined rule. 60 minutes in this sense. And the cool thing here, we built out a little class that we can still have that predict, transform type of API. If we take that data and we fit it with 3 components, and I have a wrapper function to do plotting these components, I get a sense of what I was looking for. So here, this is component 1, 2, 3, or 0, 1, 2. Here, this calendar is now displaying a probability distribution. So anything that's blue is going to be less than equal chance for this whole space. And then anything that's red is going to be higher chance. But we can see that these components are pulling out some of this behavior that we were seeing in some of these examples. For instance, component 0 has this commuter maybe going to work and leaving work with some maybe noise here. There's some kind of catch-all that's happening here. And there's this lot of weekend behavior that's happening here. I think the interesting thing here, and when I was initially going through this, was the fact that when in the model, each one of these blocks, which is the vocabulary, is treated as independent. However, when doing the fit, the parameters land in a way that makes sense to kind of the data set context. And interestingly enough, there's no reason why this square right here and this one next to it, whether it be vertically or horizontally, should be correlated. However, by using this latent component concept, we're inducing this correlation between these timestamp blocks. So some of the information that comes from here is some of the type of distributions. So at a high level, this second component is the most probable. This 0th component is the second most probable, and then this first one is the least. However, the predictions and the transformations, they happen at this document level. So in this case, these are looking at the stations. So here I have each one of these rows is reflecting the station. This first column is the raw data that's coming in at this vocabulary aggregated level. This second column is this reconstructed using that predict method by marginalizing out the components. And we can see it's a fairly representative type of probability distribution here. And the cool thing with probability distributions, there might be 0 counts, say, in this raw data. However, when you go to a probability distribution space, it's not going to be a 0, it's just going to be something unlikely. And the way that this calendar distribution came out was by a composition of latent components. So although there was the highest one was 2, and then 0, then 1 for the whole population, we see that this station here is comprised mostly of 1, and then following by 0. And then this this station right here is mainly comprised of the second one. So I think the emphasis here is that this is happening at the document level. So whether it be a station or even a lower level like a user, insights happen here, and we can rationalize about kind of this low level of interest by learning some correlation between these rows with these components. I think what's interesting for the Bayesian side of things is that there's the low data support that a lot of Bayesian methodologies really get praised for. So for instance, I'm looking at 2 different time slots, and I'm displaying them in these rows. This right here is showing 0 events happening at Saturday at 2 p.m. And we can see that it defaults to just the marginal distribution of the data set it was fit on. But as it progresses to more events, we're seeing that the probability distribution that's reconstructed based off the components are converging. And just to show you that there's only the 3 components that were displayed before, and we see that this composition of based off of this having events here slowly converges there. And similarly, if there was a different say location, say maybe at 7 o'clock on a Thursday, we see a similar behavior. However, it converges to a different component as the main part of reconstructing this distribution. There's the 2 hyperparameters that happen in the latent calendar / the LDA, and I'm using some of the terminology from the LDA here, but the document topic prior really influences the topic breakdown for a new document. So this is the hyperparameter that's used when fitting, but we can see that if there's a set number of events that happen in this block, based off of the fit, which is described by each one of these lines, we're seeing that these convergence happens at a faster or slower rate. So the other hyperparameter that is at play is the topic word prior. In my experience so far, I haven't really seen that much of an impact on the results, both in the predictions as well as the fitting. And I think it might be happening to do with the number of components that are playing. But to give some understanding of what these 2 different hyperparameters are doing, displaying some different rows of different parameter values. So here, with this topic prior very low, as well as the component prior very low, we're seeing it's very kind of sparse events that are happening. Similarly, if we turn up the component prior, then we still have the behavior, but it's only when you have a concentrated prior for this topic word where you're seeing this sense. And we're seeing there's this balance of this, both of the priors that kind of is a sweet spot that has some results that might be of use. So overall, the latent calendar project is a pip solve package, and it has the capabilities to do all of the plots that you've seen. A lot of them have kind of been hidden behind only a few lines of code. So if any of those seem interesting, check it out. But for some of the items that are on the roadmap that I want to do a full Bayesian model. I think it would be interesting to implement with PyMC. directly, and not just leave it at the kind of motivation and the data generating process. I think it would be interesting to see this population inference happening there and maybe expand upon the model even more. Also, I've seen some ways to do some incorporation of priors into sklearn transformer that's currently used. I think that would be really interesting to play around with, especially with the widely kind of used package, as well as yeah. And then lastly, trying to find some other ways to make some of these probabilities useful, and I think one of them would be conditional probabilities. That's the current kind of state. But just to wrap it up, I want to show how it fits into the marketing. So there's a few different models that heavily rely upon timestamp with identifiers. I think there's some questions that really pop up and are useful when applying them in practice. For instance, how often or will something happen again? So when you get into these churn models that can help address the user base and what is the whole user base population, depend on the formulation. It's it can answer different questions. Shout out to PyMC Marketing for making some of this CLV models easily accessible, especially from the kind of the Bayesian world, so you can get some of these population inference. And I personally used a lot of just simple conjugate models to address this and estimate this, especially when you're looking at and interested in a user level or a very low level sparse data set. But for the latent calendar, this is addressing this the flip side of this question. So if you know something's happened, when is this going to happen? So specifically, when during the week is something going to happen? And in terms of marketing, when you're reaching out to people, it's, I believe that this is a way to provide some personalization when you're looking at the user base that is active. So overall, just going to quickly wrap up with big thanks to Thomas for the invitation. And I also will shout out Juan, who's a colleague of ours that inspired me with the slides. And if anyone would like to check out some of the documentation for the package and find some of the materials that went into the slides, feel free to scan the QR code and check it out under the Latent Calendar project.
Very cool. Thank you.
And that's all I had. Yeah.
Yeah, that was really, really interesting. I love how you got around to using PyMC, right? I mean, it's amazing for its flexibility, but whenever you can and rely on, for example, conjugacy and the fact that people have already not only solved the math, but also provided a really good implementation and scikit-learn, whenever you can use that, obviously it's going to be much faster and better, right? If you can get around sampling, then it's a good idea. And I guess the other thing that I found really striking is how like these plots just are so tangible, I guess. So I'm curious how this project was perceived by stakeholders, whether like, that's amazing and we totally get it, or was there still actually some challenges in terms of explaining the solution, or did they totally get it?
Actually, I think there's a lot of because of the ease of explanation and the discussion that happens when you expand out some of these components to be, say, 10 or 20, it still keeps this heavy correlation, especially when you look at these components that are the most kind of probable across the population. And I think there's always just a lot of pointing out, oh, that's me, that's when I went to the store or something like that. And I think there's a lot of discussion that is playful that I've seen. So it's been a very easy win there. I think the calendar view is something that people stare at constantly. You know, I live by the calendar, it feels like sometimes with my Google Calendar, but internally and application, I think it's been easy to sell. But then there's always kind of the implementation. There's always the data that's going in is always going to determine the out term. So you really have to, when you're playing around with this, understand what are you trying to get at? Are you trying to see when people are going somewhere, when people are active, when people are doing this? Because what's aggregation you use to fit the model is going to just kind of show itself in these components. So that tends to be the majority of the discussion.
Yeah. And I would imagine that maybe once you have these plots that sort of already show everything that's going on in an intuitive level, that you don't even have to explain too much the details of like what LDA even is. Have you found that to be true?
Yeah, honestly, so coming from that likelihood perspective, that multinomial and this discrete timestamp, that's kind of how I address it, and the way that it's presented, I think just sells it by we're marginalizing out these components. Of course, if we want to do a deeper dive of why is this, say, prediction like this, there is this explainability factor that's really great. But when it comes to the reconstruction, it's the reconstructed item that is of interest. And whether that's using this technique or just a multinomial empirical distribution or something with conjugacy, you can arrive to the same type of result multiple ways. So
yeah. So I mean, maybe that's a hack that you found, where if the plots are that strong, you can actually get away with less explaining what the model does, because that's something that we often struggle with, right? Is like we build these elaborate models that are very powerful and cool and useful, but then we often struggle explaining it to the business side, right? But yeah, if you just show the insights from it, that actually works sometimes a lot better.
yeah, totally. I guess I would just add that, I mean, you can add this into a complicated system, especially with the fact that it's kind of sklearning components from this stage. You can incorporate it to a complicated system, and then you can complicate this explanation. But when you're just looking at it as is, I think it just provides some insights of what's going on, get a sense of this data set, and kind of the observations and some type of glance into this variable.
And is this being used mainly as an insight generating tool of like understanding the patterns, or is it also used in an automated way where like, well, we're going to use these in an optimizer to structure our fleet or whatever?
Yeah. So the generalization of it, and the fact that it's just this document level, which can be very arbitrary, I think is made it applicable in many different applications. And you can aggregate, like in this, to a location, or you can aggregate to a kind of a user level, whether that be someone doing this or someone doing that. But I think the most helpful thing with the application is that probability distribution over the calendar, especially trying to address this personalization that happens kind of at this very low level of granularity, the sparse data set, usually kind of user level. And when you're looking at just that marginal or the marginalization, you're not really considering too much about this kind of how it's built up. And you can approach it from a exploratory factor, but in automation, you can do some maybe more typical machine learning workflow there, right, to rationalize that. Yeah.
And at the end, you mentioned the connection to CLV modeling. I didn't quite get that. Could you explain to me what that idea was?
Yeah, sure. I'll bring up the chart again. So here is just that, should see my slide.
Yep.
So just how there was the gap, there was the jump from going from simulating each one of the trips. There's this conditional of, we already know that there's some activity or that trips are happening. So this bridge here is that you already know something's happening, but if you're interested in looking at this kind of from this perspective of a new person, you do have to encounter you have to incorporate this probability of it happening to then multiply these probabilities to get a sense of relative to two people. So if you compare then two people, it might be interesting to see when this person versus this person doing it. However, if you don't appropriately scale down the probabilities based off of this type of estimation, then you don't really have a sense of this full joint distribution.
Yep. Okay. And I guess the type of cluster in terms of like writing pattern that someone belongs to already tells you something about how frequently they would use it, right? Like if they are like the ones who are using it every morning and every evening, 5 days a week, right? I mean, they will have more cost than those that only use it Sunday nights. So like that could definitely feed into that CLV estimate, right?
Yeah, and I definitely would like to explore some sides there. Intuitionally, it sounds like it would work. For instance, if it's Monday through Friday, it's over 5 times versus just using on the weekend, it's only 1. You'd think there might be 5 times as much for that type of high usage. I'd love to explore it a little bit more. I have looked at it very high level, and of course, when you're looking at any of these costs that I use, it's so noisy and there's heavy variation. So just looking at component probability of commuter, whatever looks like commuter versus cost, there's always a huge band that maybe the mean is helpful, but it's high variation.
I can imagine, yeah. And I mean, one is like how much they would spend in a week, but the other one, maybe where there's a correlation, is the lifetime of a customer, right? Like maybe people who are using it for getting to and from work are much stickier than those that use it on weekends because they have other options or something. So I guess there's like a lot that you could try and relate these clusters to other variables and just try and get an understanding. I mean, yeah, granted, it'll be noisy, but what isn't? And it might provide some really interesting additional insights beyond that. So yeah, it's quite exciting that this idea seems to have some legs, extensions you can do.
I would love to, if anyone goes ahead and works on that, that would be really cool to check out. Especially like you have, you see someone use it once on the weekend, you see some, or you use, the service, some arbitrary service once on the weekend, like, and this can kind of nitpick that person out. What does that tell? I mean, it's one observation, yes, but one observation in the middle of the night may be different than one observation on a, Monday afternoon. I don't know. Who knows?
Yeah. Coming back to this idea of conjugacy, so obviously here things worked out really well. So it's interesting because like for me, that's just something I just don't think about. Like I know it exists, and for me, I sort of bucket that under like things people used to do before we had scalable samplers and had to rely on conjugacy to even like get things off the ground. So I'm curious if in general, maybe you think more about these properties and how you can exploit them when doing modeling, or was this a one-off?
So I personally, and this may be another time we want to talk. I think using conjugate models has been like one of my most used things in my career. For instance, you're always encountering counts. Like even if you say bin the outliers to based off of some threshold, you then do how many are above versus how many below. That's a proportion. and you can use a binomial model, and conjugate models have support for that. A lot of these single parameter ones have this closed form, and you can basically run this maybe smoothing or this low count, adjusting for count to some degree. You know, in SQL, you can run it, do some of this formulation, and shows up. I maybe have it just part of my repertoire, because you do have this sense of this full distribution, this posterior predictive distribution, and it may be a terrible fit, but you can at least get a sense of, you have these bounds, so if it's falling out, you can gauge. It's a bit of first step, but it's obviously not a solves every problem.
Yeah. Do you mind stopping your screen share?
Yeah, sure.
On that note of conjugacy, there was some really interesting work by Brandon Willett and Remy Louf on AEMCMC. Unfortunately, I don't think they're still working on it, but the idea was that with the computational graph that you have in PyMC, you can automatically suss out these conjugacy things, right? Like oftentimes the way it works is like you have a model and you figure that out manually, like, oh, okay, well, this is what then that would look like. And maybe you get to like a closed form solution for a posterior, and then it's like perfect. But that you have to be like very lucky, or the model needs to be exceedingly simple for that to hold. But there are nonetheless parts of the model where maybe you can exploit conjugacy and just get vastly faster inference. So I thought that was a really interesting idea to write essentially a pattern matcher that would like identify these parts in the model where you could exploit conjugacy and derive like a sampler that would be much faster. So yeah, if anyone wants to check out that repo, it's in the Sarah Devs AEMCMC. In principle, that should work with PyTensor too. But yeah, so when you need to go to series scale, right, then you do need these tricks. Like currently the samplers run, I mean, I continue to be like amazed how fast they run, especially once you bring in GPUs. We run this on like hundreds of thousands of data points, sometimes millions of data points, but nothing above that. But yeah, I would imagine that like the LDA thing, I mean, people have run that on Wikipedia, right? So you can run this on like terabytes and maybe even petabytes, and there's like all these computational tricks of parallelizing it. So was that actually like important for the scale of data that you're working with? And yeah, have you like sort of tested the limits of that approach, or can you say something about that?
I haven't really hit much of the computational difficulties on this at the moment. Obviously, there's so many implementations of LDA out there, and the aggregation that, of course, I exposed through my my API. And you don't have to have this event level data set in your in memory. Stuff like this aggregation and this vocabulary creation can happen in SQL too. And then, I don't have it written for you, but, using some of these parallelized implementations of it might be kind of interesting way to do it. So if there was a bottleneck, it might be able to, bridge the aggregation into SQL as a way to lower the memory, because in this example, 6 million rows went down to 1,500 rows, and it just has, some sparsity to it, but it's a large reduction. And then for the modeling side, there are different implementations, but I really didn't have it to hit the bottleneck yet.
Yeah, and I mean, I'm not terribly familiar with LDA, but I do know that it's a very large research topic, and where many different extensions and computational tricks to scale it to crazy amounts, and also implementations to make it scale, and like out of memory kind of computations, as well as like hierarchical extensions like hierarchical LDA. So yeah, I guess whenever you have and what I thought was so interesting here is before I was like, well, I don't really work with text data, right? So I was always like, okay, it seems like an interesting model, but I don't have any use case for it because I don't usually work with text data. But what you showed is like, well, it really doesn't need to be text data, right? As long as you have the multinomial likelihood and you want to cluster on that, then it's a great choice. So the application is much wider than I had assumed going into this.
Yeah, I totally agree. I think if you recognize the multinomial distribution, then I mean it's there. I did 10 lines of code to implement it, and if you define some aggregation based on vocabulary, then you could give it a shot and see the application. Interestingly enough, yeah, if you reduce it to that same problem, then you can reap some of this work that other people have done. So it's a bit of a shame that the selling for LDED, I'm not really sure how the context of how it only got to NLP. You know, and sklearn's implementation is all like specific to vocabulary and documents. So you know, it might push people's mind into that way, but you know, I don't want to rewrite the class, but it's easy to just inherit it from it and make use of it, even if you have to do some mental gymnastics to make sure that this word goes to this one and this, you know, translation.
Yeah. So you have the repo out there, right? Presumably it's, I mean, it has the plotting functions. The model is probably just, well, what you showed, right? So you just inherit from the scikit-learn class and add a couple of wrappers.
Yeah. The cool thing with using sklearn is that it works into the sklearn pipeline. So if you want to use it as a dimensional reduction technique, that transform is what is used. So you get these component probabilities, and you could then use a predictor on the end. But for the code base, a lot of it was just I think it's 1,000 lines of plotting functionality, and just I wrapped it. I've been liking using some of the pandas extensions, and just everything is now part of a property of a pandas object. So if you just import the package, you get a lot of these goodies for free on this kind of typical data structure there. But a lot of the code is just, you know, sugar coding and aggregation and stuff like that.
Yeah, I love the elegance and the simplicity of it. Here we are like building these crazy hundreds of lines of PyMC models, and then you come along just like import scikit-learn and have something that scales much more. It's cool. And I guess you're looking for contributions to that package, so the issues that people who are interested might pick up.
If someone's interested and wants to play around with it, I would love to have some feedback and see some other use cases. I was playing around with the Chicago bikes, which is similar to kind of the business I work in, but I was touring around with just timestamps with UFOs, looking at different transactions at a customer, and just was playing around with some other timestamp. But it's could have applications and a way to just understand what timestamps you're working with. So if anyone wants to play around with it, I love feedback.
Really, whenever you're working with timestamp data that is cyclical, is that it? Like, because it's not just time series, right? Because then there might be Christmas seasonality effects. Here, you're much more like, well, every week is more or less the same. And is that the how I would classify my problem? It's like, okay, I have timestamps and it's like repeating.
Yeah. Yeah, so the repeated type of behavior there would be, if you're doing any type of prediction into the future, you would have some type of assumption at the moment that this week or this time window is going to reflect the time window you're maybe extrapolating towards. So in implementation, if you are concerned about seasonality or heavy shifts or that assumption breaks, might be weary there. I know with all the LDA implementation out there, some of the ones you mentioned, like the hierarchical LDA, I don't know, there might be a way to correlate the parameters over time and address some of these gaps. Maybe a PyMC version, when I get down to that, would be incorporating temporal parameter correlations. That might be really interesting. And inference on like population components over time. That would be a cool visualization. So,
right. Yeah, that is actually a good point, right? I mean, in those writing patterns, you would also have strong data facts, like New Year's Eve will be very different, even if it's a Monday from other Mondays and things like that. Cool. Well, I thought that was very inspirational. Thanks so much, Will, for coming on and telling us about latent calendar allocation, LCA. You heard it here first. And yeah, hope everyone here enjoyed it and learned something.
thank you, Thomas, and thanks for everyone for joining.
Bye.
Take it easy.